All right, so last time we started section 3.4. We didn't finish, but we started section 3.4, which is rate of change of composite functions. And we talked about composite functions as being this sort of function embedded inside of another function. And the way that we do a derivative of a function like that is we take the derivative of the outside and we rewrite the inside exactly like it already is. And then we multiply by the derivative of the inside. The first example, I'll just remind you what we did, and then we'll jump back into new ones. So when we looked at this function, we identified the inside as being everything inside the set of parentheses, and I made it a yellow blob. That's what I really did. And I said, what's the derivative of something raised to the power 5? And we said, well, we'll pull the 5 down and we'll decrease the 5 by 1, so making it a 4. And the part that's underneath the yellow stayed exactly the same, right? So that part under the yellow is exactly the same on the inside. And then we need the derivative of the part in the yellow, which was 3.2, and we multiplied that on the outside. Okay, we multiplied by it on the outside. So that's the basic idea of looking at composite functions. And we actually are on example E, so we'll jump back over to example E to continue working. So this is an example of one where it does not look like there is an inside function. I have a numerator, I have a denominator, there's no visible parentheses, I don't have something raised to a power, I don't have the traditional things that I was looking for in the previous problems. However, in some of the operating systems of your calculator, and even if it doesn't actually have the notation, there are understood grouping symbols around that denominator. All that denominator is grouped together, right? It's all down there. So that denominator actually is the inside function. And instead of having it written like this, because we also don't have any derivative rules for what to do with denominators, we're going to bring that denominator up to the numerator, x squared plus 1. And in order to bring it up to the numerator, we have to have it with an exponent of -1. So this is just rewriting what's already there. This is not calculus. This is an algebra idea of being able to shift the location of something in the denominator to the numerator, or you could do it vice versa if you were needing to do so. So then when we do our derivative, the inside function, of course, is this piece right here. So we have a -1 on the outside, and I'm going to bring my -1 down with the 42. So I'm going to have -42. And I'm going to decrease my exponent by 1. So what is -1 decreased by 1? -2. The inside part stays the same. I don't know if I can actually now undelete my yellow. Maybe I can. It did. Good. Well, almost there. And I rewrite the inside. The inside never changes when I'm taking the derivative of the outside. But I do multiply by the derivative of the inside afterwards. So what is the derivative of x squared plus 1? 2x. Okay, so this piece is the derivative of the outside, and this piece is the derivative of the inside, and they are multiplied together. Okay, do you know what f is the equation of? What kind of a model? We've talked about them. No, those are rational ones. It's not like that. What if it didn't? Yeah, we moved on to F. What if it didn't have this on the end? Do you recognize it now? What is it? Exponential. Nope, not exponential.
That's just the bottom part.
The bottom part has an exponent in it, an exponential portion. Ooh, you're so close. Not logarithmic, but sounds like logarithmic, but isn't. Logistic. This is exactly a logistic model. Yeah, This is a logistic model. Even with the plus 84 on the end, it's a logistic model. What it does is it just takes that graph and it shifts it up 84 units, right? So it's still a logistic model. It's just not a logistic model with the limiting value on the x-axis. So just like on this last one where I moved the denominator up to the numerator, I can do that here as well. It's just a messier problem. So 492.7, because now I have 1 plus 0.67 e to the negative 0.49 x raised to the negative 1. There's still plus the 8407 on the end. Here's the primary reason why this is messier. Is because I have this inside function. I mean, you see it, it's all inside the parentheses, right? But there's actually another set of parentheses within that parentheses. Do you know where it would be? Yeah, it's the exponent. The exponent's another inside function. So this one's going to have 3 parts. We're going to have the derivative of the outside, right? The stuff with the exponent negative 1. We're going to have a derivative of the inside, the first big inside function, ignoring the inside parentheses in yellow. And then we're going to have the derivative of the piece that's highlighted in yellow or bracketed off in yellow.
So you need to have those parentheses in yellow for it to count.
Well, you don't need to have them there. They're understood to be there, but probably for your own benefit, it's easier to see it if you write them in. Yeah. All right, so we're starting with the derivative. Whoops, that's not what I meant to do. By ignoring the part that's the inside, everything that is shaded yellow, ignoring that part. Okay, so I have the derivative of the outside where I've got the negative 1 power that I'm going to bring down. So for starters, this is g prime of x. Please make sure you relabel. It's not just g of x again. It's g prime now. The negative is going to come down, so I have negative 492.7. In a minute, I'll write all this again, but what's my new power? Previous power is negative 1, so negative 2. 1 less, yeah. And then what's the derivative of the 84.07? 0. Yeah, so I don't have any other piece out there with it. Now the part that's highlighted in yellow will get rewritten like that. All right. Now, the part that's highlighted in yellow, that's an exponential function. Mark mentioned that one earlier. It's exponential, so we're going to take the derivative of an exponential function. Well, the 1 plus at the beginning, what's its derivative? That one's 0, so I don't need to worry about that. Then I have this piece. So the 0.67 is a constant multiplier, so it comes along for the ride. What is the derivative of e to a power? E to the power. And the power remains unchanged. It's another inside function that I'm not going to manipulate until I take its derivative next. And that's where I am now. So am I off the screen yet? I'm awfully close. Let me shrink this just a little bit. Whenever it projects hardwire through things, it projects larger than my screen. All right, and then what's the derivative of the exponent negative 4.49x?
Just negative 0.49,
Right, just negative 0.49. So there's 3 pieces here. This is the derivative of the outside. This is the derivative of the first bigger, massive inside function, everything that was previously was in the denominator. And then this is the derivative of the inside exponent of the denominator itself. So there's 3 pieces because there was 2 inside functions, outside and then 2 insides. Okay. All right, you ready for the last one? G. G looks so much cleaner than the last one I just did, but it's really weird looking too. It's weird looking because it's got an exponent raised to an exponent. I mean, it's not an exponent times something, right? Like most of the time we did. Like the last one had the exponent of x times the negative 0.49. It's not multiplication, it's actually a power. So if we were to look at this, do you know where the parentheses should go? Mark?
Between X and 4.
Not between them, but around them.
That's what
Like that. They should go like that. Yeah.
couldn't you also write like 5 raised to the X and then outside the parentheses, like put that raised to the 4?
The problem is that if you write it like this, what that actually means is that the 4 and the x are multiplied, which means it's actually like this, which we know it's not. That's what the parentheses would mean with exponent rules. But that's a really good question to differentiate between the two. Because you're kind of left trying to make that decision, right? Do the parentheses go around the 5 and the x part, or do they go around the x and the power 4 part? And if you try to put them around the 5 and the x part, the parentheses are understood to mean that we would multiply the exponents. So this isn't the way we would want to do it because of that notational part. Okay, so we have 5 to a power. That's my outside function. What's the derivative of 5 to a power? It's from section 3.2. Okay, so it's 5 to the same power, and then it's times natural log of 5. That's the power, not the power rule, excuse me, that's the exponential rule, the b to the x rule. Now I have the part that's the x to the 4th rule. So what's the derivative of x to the 4th? 4x cubed. And that would be finished at that point. Okay. So this is chain rule. Chain rule always looks like there's something embedded inside of something else. If you look carefully, you have to make the decision, where are the understood parentheses going to be? Try something, see if it works, and if the process doesn't work with the parentheses there, make an adjustment until it is the right location.
Could you go back to that first slide where it actually defines the chain rule? I never got that there.
Yep. This one? Sure.
I'll just take a picture of it so you can.
No problem.